In section 6-1, we're going to be talking about arc length and the area of a sector. And you can think of a sector as a piece of pie. So what we have is an angle. It makes up some portion of the whole circle, so we're going to call that theta. And we have a radius of the circle r. And arc length is denoted by s. This is not a 5, it's s. And they use s in math for the length along the edge of the circle, the arc length. The one thing that you need to know is that your central angle theta, this guy right here, that angle, in order to use these formulas to find arc length and area, has to be in radians. So you can't use the formulas I'm about to give you unless you convert your angle, if it's in degrees, to radians. So it has to be in radians to use the following formulas. So let's start off with arc length. The formula to find the arc length s is equal to the radius of the circle times the central angle. So again, remember that the central angle has to be in radians right here. So in this example, you're asked to find the arc length of a circle that has a radius of 21 meters and a central angle of 15 degrees. So we're going to use this formula right here, but we're going to convert our angle to radians when we do so. So arc length is equal to the radius, which is 21, and then we're going to multiply it by our angle of 15 degrees, and if you remember from last chapter, to convert that, you're going to multiply by pi over 180 to convert that to radians. So when you go ahead and multiply that out, you multiply top to top, bottom to bottom, so multiply the 21 times the 15, I get 315 over 180, which reduces to 7 pi over 4. And we'll say that the arc length is 7 pi over 4 meters, so that would be S. Okay, so moving on to finding the area of this sector. So again, this time we're going to find the area of that piece of pie. The area is equal to 1/2 your radius squared times that central angle. So in this next example, we're going to find the area of a sector that has a radius of 45 meters and a central angle of 4 degrees. So again, we have to convert our central angle to radians. So to find the area, we're going to go ahead and use 1/2. We're going to square our radius, which is 45, and then we just have to multiply it by theta. But in the process, we have to multiply 4 degrees times pi over 180. So we're basically just going to multiply all the tops, so all of these, over all of that. Here's what you get. So you get 8100 pi over 360, that's the 45 squared times the 1 times the 4, leave it in terms of pi, over 2 times the 180, and then when I go ahead and reduce that, I end up getting 45 pi over 2. So leave your answers in terms of pi, and because this is area, the units for area are not going to be meters, but square meters. We want to figure out how much area does this cover. So the next thing we're going to look at is circular motion, and I have a diagram here, and what it's going to involve is motion. So imagine this being a rock tied to the end of a string, and you were going to go ahead and move that around your head. You're going to rotate it. It's going to move a certain angle theta, so you'll have a certain angle, so wherever it terminates, theta, and that's going to be your central angle. So it's going to rotate at a certain angular speed, and then it's also going to cover a certain arc length. And the arc length is going to be its linear speed here. So there's a couple formulas that we're going to talk about, and one is called the angular speed. How fast is this angle changing as you rotate it? So let's start off with some vocabulary that we're going to be using. First one is the angular speed. So it's just the rate at which the central angle is changing. So as this rock moves along that path, this angle is also going to change with it. So the angular speed is, there's a formula, and here's what it is. And so the formula is for angular speed, they use the Greek letter omega. It looks like a W. A lot of people just say W equals, but you technically are supposed to say omega. The angular speed is equal to your angle, which I'll give you a formula for, over time. And in order to find your angle, you will go ahead and take 2 pi. So your angle is equal to 2 pi, because if you think about it, In one complete revolution, there's 2 pi radians. Remember, our central angle has to be in radians. And then you're going to multiply that by the number of revolutions. So I'm going to put the number of revolutions. So you're going to multiply 2 pi times the number of revolutions. I'll put a little number sign for you. So now we're going to talk about linear speed. So how fast is this object moving linearly? If you were to put it on the ground, or if it was in the sky and you're rotating it, how fast, what would its linear speed be? And let's talk about what it is. So linear speed is the rate at which the distance traveled is changing. And there's a formula for this. The linear speed, also known as the velocity, is equal to the radius of the circle. It could be a bike tire, it could be a fan rotating one of the blades on the fan. So it's the radius times that angular speed. Remember, the angular speed was omega. So if you want to find that linear speed, you just take the radius of the circle times its angular speed, how fast that angle is changing. So let's go ahead and use those formulas in this example. So we have, let's say, a compact disc, has a 12-inch diameter and spins 45 revolutions per minute. That's RPMs. So you're going to find both the angular speed in radians per second and then also the linear speed, how fast it's moving on the outside. So let's go ahead and start with angular speed. If you look back at the formula, how fast that angle is changing, is you're going to use omega. And omega was equal to theta over t. And remember, to find theta, we have theta equaling 2 pi, which is 1 revolution, the radians in 1 revolutions, times the number that we have. And we're just going to go ahead and plug it into that formula. So omega is equal to, all right, we have theta. And theta is equal to 2 pi from the formula. And we have the number of revolutions, which matches up to right here. These are your revolutions. And our units are revolutions per 1 minute. So what I'm going to do is multiply it by 45, because there's 45 revolutions. And then our time, which is right here, is per 1 minute. So if it was like 45 revolutions per 2 minutes, it'd be over 2. So then all you go ahead and do is multiply. So what you end up getting is 90 pi, and this is going to be radians, over or per 1 minute. Now, one of the things you're going to need to do is you're going to need to look at what the units are. I want the answer in radians per second. Well, what you would go ahead and do is say, oh, I know how many seconds is in 1 minute. I'm going to change this to 90 pi radians. And then there's 60 seconds in 1 minute, so this is going to convert it to seconds. So then all I have to do is go ahead and reduce that. So I'll basically get 3 pi over 2 radians per second. So basically, if this thing were on a circle, if you think of the unit circle, so here's 3 pi over 2. Here's your object. It starts here. This angle is changing 270 degrees every second. That's what that means. So a second goes by, it goes 270. Another second goes by, it goes another 270, and so on. Okay, so now let's find the actual linear speed. So that's going to be the v, or velocity, or linear speed, is equal to your radius times your angular speed. Well, we already found our angular speed. We did that in this problem. All we have to do is multiply it by the radius. So the problem tells us that it is a 12-inch diameter. Well, that means that the radius is actually going to be 6. So when I go ahead and plug it into the formula, the linear speed is equal to the radius, which is 6, times its velocity. Remember, it was changing 3 pi over 2 radians per second. So I'll put rad per second. And this was 6 inches. So when I go ahead and multiply all this out, I can do 6 times 3 divided by 2. Or 18 divided by 2 is 9. So I get 9 pi, and then I have my units, which are left over, inches per second, which is exactly what I wanted. So I have inches per second. I don't have to worry about changing anything. So if you want to quantify this a little bit more, 9 times pi is like 28.3-ish. inches per second. So this thing is moving, if you think of how much 28.3 inches per second is, it's going 28 inches about every second. So in this last example, we have a bike wheel that is 30 inches in diameter and rotates 150 revolutions per minute. And our goal is to find the speed at which it's traveling in inches per minute. So when they give units inches per minute, that's going to be a linear speed. So we're going to go ahead and start with the formula for linear speed. What's its velocity traveling on the ground? So v equals, or linear speed equals, the radius of the circular object, so in this case the bike wheel, times its angular velocity, or its angular speed. So starting off, since this bike tire is 30 inches in diameter, we're going to go ahead and use its radius. Its radius would be 15 inches. So we would get the velocity is equal to 15, and now we need to find the angular speed. So we're going to go ahead and use the formula to find the angular speed. Remember, it's theta over t. And to find theta, we're going to go ahead and multiply 2 pi times the number of revolutions. So we have the number of revolutions as 150 revolutions per 1 minute. And so we're going to multiply it by 150 revolutions. So I'll just put 150 revolutions per minute, per 1 minute. And this is what we're going to multiply. So I get 2 times 150, so I get 300, and then since this is the angular speed, the angle is in radians per 1 minute. Alright, so we're just going to have radians per whatever the unit of time is. And this is going to go ahead and get plugged in to omega right there. So we're going to multiply this by 300, and then pi, and this is going to be radians per minute. And remember, this was inches, so I'm going to put the little inches to remind me what I have here. Units, it's all about the units on this. So when I go ahead and multiply 15 times 300, I end up getting 4,500 times that pi, and then the units are going to be inches per minute. And that's exactly what the units were that were wanted for this problem. Okay, that's a wrap. I will see you guys tomorrow. Have a good evening.